Hello, my name is Alex Mathewson. Throughout this presentation, I will provide you with an interpretation of the mathematics and numeracy used in the Australian Army Aviation Corps. I will provide you with a range of mathematical problems that could be presented as an inspiration for the beginning of a STEM unit. Within the Australian Army Aviation Corps, there are a range of roles that can be adopted, whether they are flying, maintaining, or in a support role. They will work closely with an impressive fleet of helicopters. These helicopters include Black Hawks, Chinooks, ARH Tigers, and the MRH-90. When I first began to think about what mathematics would be involved in the workplace for Army aviation, questions started coming to my mind such as, what problems would these employees be facing on a daily basis when working with helicopters? Some of those problems could include topics like speed and distance. And with that knowledge of speed and distance, it would be essential to find out how much fuel is needed for these tasks. The weight distribution of passengers in the helicopter would entail mathematical thinking to ensure that the helicopter flies in a straight line and stays upright. But how do we know how these problems can be solved? I was lucky enough to interview the head of the Royal Australian Electrical and Mechanical Engineering Corps, Major General Andrew Mathewson. Andrew Mathewson grew up on a vineyard in Mildura before joining the Army as an apprentice fitter and turner in 1980 at age 15. He entered the Royal Military College in 1986, graduating from the Royal Australian Electrical and Mechanical Engineers in mid-1987. Early postings were predominantly technical. After completing his bachelor's in mechanical engineering, Andrew completed his master's in science, business administration, and defence studies. Andrew is currently the head of helicopters and tactical unmanned aerial systems in the defence. In the beginning of Andrew's engineering career, he initially completed his bachelor's in mechanical engineering. Here, the core of his mathematical competencies within aviation were formed. Due to Andrew graduating from university over 20 years ago, I've conducted extensive current research on the required mathematical knowledge in order to study the multiple degrees that Andrew had completed to get where he is today. Now, what is mechanical engineering? Mechanical engineering involves design, manufacturing, and optimizing specialist machines and processes. As part of their Bachelor of Mechanical Engineering study, they learn how to solve important problems. The core courses in mechanical engineering teach them to develop solutions using robotics, new advanced materials, the fundamental laws of energy generation and transmission. The degree could lead to work in everything from power plants to air conditioners, aircraft engines, and race cars. Although mathematics is incorporated into most engineering subjects, engineers at the Australian National University are required to undertake only 2 math-centred units, Mathematics and Applications 1 and 2. Here, the learning outcomes are to explain the fundamental concepts of calculus and linear algebra and their role in modern mathematics and applied contexts. Demonstrate accuracy and efficient use of calculus and linear algebra techniques. Demonstrate capacity for mathematical reasoning through explaining concepts from calculus to linear algebra, and applying problem-solving calculus and linear algebra techniques applied to diverse situations in physics, engineering, and other mathematical contexts. I asked Andrew about the key mathematical concepts incorporated in Army aviation. He said that a lot of mathematics is used in the engineering calculations, particularly in relation to stress and fatigue on components of the aircraft. A more practical example of this use is mathematics in the work done to double-check the aircraft computer calculation on fuel usage. Everyone needs to understand the mathematical relationships and to complete calculations rather than rely on the computer with no understanding of context or risk. For example, they use algebraic algorithms to determine the influence on external factors such as wind speed, altitude, and the load of fuel usage. They use geometric analysis to determine sling loads, and in all instances, estimation remains important to check the calculation results are close to what they expect. Andrew mentioned that a common calculation that is implemented while working with helicopters is working out how much fuel is required for helicopters to travel from one location to another. This calculation then changes if a sling load is required. I asked Andrew about how much the utility of this equation has changed over time with technology. He said that fuel use equations are normally done by the computer on the helicopter, but it is still extremely relevant to understand the mathematics just to double check the machine. The equation displayed on this slide was provided to me by Andrew. I will draw on this later. Now is the time that we apply this knowledge into an educational context. How can we use this in a classroom as a tool for learning? STEM, being science, technology, engineering, and mathematics education, is an umbrella for the Australian curriculum learning areas of science, technologies, and mathematics. This discussion about Army aviation provides your class with a range of opportunities in these curriculum subject areas, leading to open-ended, student-initiated tasks. As educators, we need to explain the mathematical relationships that exist in everyday workplaces. Therefore, rather than presenting the students with a formula for them to insert data, it is far more important to understand the relationship between each of the factors. As a practical example, here the pilot needs to be comfortable that he has enough fuel to complete their mission. The fuel consumption rate will vary depending on the flying conditions, like a headwind, and the load carried by the aircraft, such as a sling load. By multiplying the fuel consumption by a planned distance, the pilot can calculate the fuel needed. Of course, some spare fuel will always be needed to be there in case of emergencies such as taxiing or any delays where the helicopter may need to hover. Before presenting the problems, as a whole class, an inquiry-based discussion should take place to understand the mathematics and technology surrounding aviation. This problem provides a simple equation to find out the fuel needed in order for the helicopter to travel from one location to another. Students should be encouraged to draw diagrams to ensure they fully understand what the question is asking them to find out, as well as using estimation throughout to make sure the answer makes sense. To demonstrate their understanding, the students should solve the problems using the following steps. First, they should draw a diagram of what the problem is asking. They should then move the units from the questions into the provided formula in order to find out what is missing. The student should then realize that in order to find out how much fuel is required, they will need to multiply the fuel usage, which is 1.5 litres per kilometre, by the distance they are travelling, which is 320 kilometres. When multiplying decimals, it is often important to estimate what the final answer might be. We know that the answer will be more than 1 times 320, which is 320, and less than 2 times 320, which is 640. So the answer should lie somewhere in between 320 and 640 kilometres. The students should then work out what 320 multiplied by 1.5 is. The final answer should be that the helicopter will need 480 litres of fuel to travel from Sydney to Canberra. Once understanding is demonstrated, you should then introduce a variable into the situation, making a different and possibly more challenging problem. So this problem requires the students to expand on their understanding of helicopters through solving a problem that involves more unfamiliar language, such as a slung load. Again, the students should be encouraged to draw a diagram to ensure they fully understand what the question is asking them to find out. Due to the length of the question, it may be difficult for the students to understand what the problem is asking. So moving through the solution one step at a time would be especially helpful in this situation. First, they should draw a diagram which will illustrate what the problem is asking. They should then move the units from the problem into the formula that is provided in order to find out what is missing. The students should then realize that in order to find out if they have enough fuel, they will have to work out how far the fuel they do have will get them. Therefore, they will need to divide that 500 litres by the 2 litres that are used per kilometre. Half of 500 litres is 250 kilometres. So the helicopter would only be able to travel for 250 kilometres, which is 70 kilometres away from where they need to be. And therefore, there is not enough fuel for the Black Hawk to fly from Sydney to Canberra with a slung load. Working through this problem with your students provides them with the opportunity to develop numeracy capabilities, aligning with the Australian curriculum mathematical descriptors for Year 6 and 7, as well as building the fundamental skills needed in mathematical specialties and professional applications of mathematics. It develops the numeracy capabilities that all students need in their personal work and civic life, and provides the fundamentals on which mathematical specialties and professional applications of mathematics are built. The strategies implemented throughout the problems were visually representing the problem by drawing a diagram, solving a somewhat similar problem before attempting a more difficult one, as well as estimating throughout to ensure rational answers are reached. And finally, the strategy of implementing mathematics within a real-world context would provide the students with a base for further understanding the concepts within engineering. Initially, I had a lot of difficulty narrowing the specifics of mathematics that would be used in this workplace. I could think of mathematical problems that Army aviation engineers would face, although my knowledge could not extend to understanding what specific mathematical capabilities could be used to solve them. Computers solve most of these problems, and therefore most calculations made to confirm these problems are often overlooked. Through additional research, these calculations are often overshadowed by the technology as well. Major General Andrew Matthewson's knowledge has enabled him to become a meaningful contributor to society. Some examples are serving as a peacekeeper in Kosovo and Bosnia, as well as being responsible for a budget of $8 billion of taxpayers' money for the purchase and support of Australia's Defence Force helicopter fleet. In 2015, he was made a member of the Order of Australia for this work. I hope this presentation has provided you with an understanding of a portion of the mathematics used within this unique workplace that is the Australian Army Aviation, and how this can spark a basis for discussion with your students?